Okay, so let me welcome you to then to network security, the lecture. First, I want to say some words on the organization. Maybe some. Okay, so we have basically just one lecture in a week. It's on Monday. Oh, the room is not correct. Sorry, I will just correct it. So it's always in this room. And then we will have a second exercise that takes place in the week. So we have two slots for the exercises. They will take place in the networking lab in L1 310. I will also update the YouTube link for the recordings. But for the lab exercises, so the idea is that we have two exercise slots a week, and you only need to book one. So you just have to visit one. It's just that for the opportunity, for the options, if last time we had 30 students and there were 16 places in the lab, then they cannot all join at the same time. So actually, yeah, the numbers were rising and going down. So now it would all fit in one time slot, but it's hard to predict up front. So actually, we have 4 time slots, so there's really some room. But I think with that amount of students, this will not be needed. Let me just show you in OLAT how this looks like. I just open one moment. So you find all information on OLAT anyway, and also the options to record, to register for exercise that you can also do online. So if you go to network security, and what you have to do, so here you will find over the course of the lecture, some recording, some announcements. Maybe one moment just to check. Okay, yeah, you will find the announcements. You find the teaching material here. So actually, it's already uploaded to quite far part, but especially at the end, there will be some kind of option to change some topic, especially this data in use can be also replaced by some other elements if it's relevant to pick up. Okay, and yes, for the exercises, here we have the lab registration. I think you have to register in order to be able to select some of the time slots. So what happens here is that's not yet. I'm not really sure whether. So I will update that. So what you need to do is to go to the lab schedule, and here you should find all the relevant exercises to take place. There's already one I see with for today. That's okay. And you can register. So so let's open that again. I didn't want to register that. So if I, for example, take on your role, and then I go to lab schedule 0, then I can select some of the places that I would like to join in. But actually, you would just need one. Typically, 1 hour one slot will be sufficient. And if you find that this one doesn't fit you, but you want another one, then you can select. But please only select those where you also come. So don't select one and don't come. That's a combination that doesn't work well. Okay. So have a look for which time slots to register. Actually, they should all reflect. I did not yet register. That's what you see if you did not register. Otherwise, the dates reflect what is available. Here is the schedule. So that already takes into account if there are some public holidays or similar. Okay. How does the lecture take place? Let me just also see what I already updated. Here you find also you'll find the lecture recordings. I think that's already updated. Yeah, it's already the newest link, that's right. So 2025. So OLAT is always most up to date, and also if there are some in between updates, check OLAT, or at the last resort Webuntis if there's some kind of changes in the organization, if some dates will maybe not take place. For example, in May I will be not there. It will not, will not cover you, will not affect you. It will only affect Tuesday to Thursday, but I keep the dates available in Webuntis, and in OLAT are the updates. So this QR code I will also update, and then it will be fine. Otherwise, you find also the other recordings of lectures online on YouTube or on some kind of personal website. It's a little bit difficult to put it on the TH Bingen website to include some YouTube videos or some playlist, so therefore you find it under my personal website. Okay, for the exam at one time, it will be at the end of the lecture time, of obviously in July somewhere, August, register in Campo, that's nothing new. And also the OLAT should be up to date, I think. I updated the slides, yes. Okay, otherwise there's no special, so that's basically how it will take place. We will have the lectures, 13 or 14 we will have during the run of the semester. We will have 7 exercises in total. So, and what we do there will be part of the exam, so there we can cover some other topics that we are not able to cover maybe in the lecture, but the exercise parts are of course also part of the exam. And in contrast to Krone, there's no enforcement to participate, because also now everything is quite, I mean, in Krone you had the Studienleistung where you needed 6 out of 7 exercises. Here it is not enforced, but because the topics are as similar as the lecture topics part of the exam, then yeah, there's the call to participate. Okay, so what will we have a look at? Yeah, maybe some other questions on the organization. Do you have any questions with regard to that? Otherwise, let me just see. There's maybe to go through it. Okay, so I will come to the topic later. Let's say here as I said, so how's the procedure? So please register in OLAT as a lab participant. Then you can select from the schedule. Select one appointment per lab exercise. There are 7 lab exercises with 2 to 4 appointments each. It always varies on if there are some public holidays and the specific exercise days not taking place. Then sometimes I think we also have the one exercise with only 2 appointments each, so select one. And the idea is that you come to the exercise, then to the lab, and with some support and with some help, ideally of course alone, but I'm there to support you in setting up the questions and then providing you some support in finding the solutions.
Sorry.
Yes? The dates are not updated, I see that. So let me just, they are not updated. I had 2 versions in conflicts with my slides, and obviously I took the wrong one. But I have an update. Let me just see, where do I have the updated slides? The dates are not updated. You have to deduce 1 hour of 1 day. 1 moment. Let me just find the right slide. Yes. Okay. And I will update the slide. So basically, basically it's all minus 1 day. So it starts from 7th of April to 18th of April. You always have to deduce one day. So the task sheets contain the questions. Please download them, register for this lab exercise, come to the appointment, perform the task, answer the questions, meet fellow students, talk, exchange, work together, ask questions, and the solution should be inserted into the document, and then the solution should be uploaded by this kind of number of students. It's easier to give feedback to all of you. So it will be on a punctual basis. So basically, I will select I will give feedback partially. I don't promise to give it to everybody, but by this overview of students, this is manageable to give much more feedback. Let me just show you some example how this looks like for this current week. Let me just see. Is somebody of you already registered here? Because I also really ask you to give me feedback if it doesn't work for you.
It should have worked. So
if
you can read the exercise.
Okay, you can. Okay, that's good, because it's I don't have the same view as you have in OLAT, and therefore I have sometimes struggles to identify that you didn't get the file, but I see it. So the first task, because last time it was noticed that it is good to refresh some kind of the Linux background and how to use that kind of machines. There's some kind of interactions or how to interact with Linux. If you're familiar with it, then probably this is something that might be redundant to you. But the last time when we didn't have this exercise number 0, we had the issue that there were some assumptions from my side how to use Linux that I assumed people know, but they didn't. So that's why we have this kind of setup, how to basically download a file, how to use LibreOffice to make some changes in it, and how to upload it again, how to interact with the shell. And the idea here is when there are some questions in the text, what you can do is, so first of all, to download it, the file, then you can I edit it? Yes. Take some kind of color that is easier to differentiate. I don't know. This is my answer, and then you can download and upload it. So basically, to upload it, your modified version, and then I get all the uploads and can have a look at them and give feedback. So that's the idea. So download the file, modify it, add the answers, and upload it again, and then I can give you some feedback on that. Okay. Okay. So there are different approaches how you can do it. So basically, the final goal is to upload the files. So basically, the minimum. So one of the approaches is to come to the exercises, do it there, everything is prepared there, all programs are working. Otherwise, because I also want to support the opportunity if you have to work, if there are some time conflicts, you can also do it in some kind of virtual environment or some windows on your own device if you know what you're doing. And so to me it doesn't really make a difference where you do it or how you do it. The important part is that you do it and that you know that you learn from the process. Okay, yeah, while you are there, we will also have some kind of you will have some kind of I will show you the credentials and how to log in. Okay, so that's still that's the wrong slide. So basically, it's all 1 day earlier. I had this C file conflict that really annoyed me because I made all the changes and then it changed. Yeah, tried. Yeah. Okay, and this, I just uploaded changes for this slide. So basically, on Friday evening of the last week, of a 2-week period, you asked to upload it. Yeah, so if this is the first lab, yeah, it's did not change this one. So I will update it. I will update the slides today, and you will find it in OLED. So the first lab runs basically from today until next Friday, and deadline to submit is Friday evening, 11:59. And on Saturday, I will upload the slides. And possible dates are this Monday, 7th. Yeah, so I will update it. So if you register for an appointment today, I saw somebody was registered, or 2 persons, please show up, implement the assignment, upload the solution, or do it. So if you do not manage to finish in time, maybe for some of the later tasks that will happen, then feel free to continue at home and then upload at the end. Okay. Yeah, about the point of proactive or some kind of hacking approaches. So network security and IT security is a very broad elements, and there are lots of opportunities. I mean, there are different kind of perspectives to take on. One is the defensive, on how to minimize vulnerabilities, how to detect ongoing attacks, how to prevent them, how to counter them. There's the other perspective of the offensive approach to identify weaknesses, misuse them, and to induce some kind of malicious activity on that. I have to say it. Let's put it out. We will have a look at how attackers proceed, and it's sometimes also the question of who's considered an attacker, depending on who's attacked. So there are various examples when the same procedure is illegal, or it's illegal and mandatory. So just be considerate. There are many attacks and many actions that are punishable by law, even if they do not do real damage, if it's just a joke, and even if you just want to test something. So be aware of what you are doing and what machines you are doing it with. So of course, we will have a look at, just want to make sure that everything is clarified before any kind of activity is done. And so let's see what in this kind of realm and what kind of boundaries we can do. But because of course it's legitimate to ask for some kind of potential approaches to do some potentially malicious stuff in order to identify where the weaknesses. So it's required or somehow relevant and essential as well to really know from the attacker side the perspective in order to understand how the defenses can be done. Okay, so some of the prerequisites that we need for this course. First of all, basically it's computer, so network security, so we need some knowledge about networks. The layering, IP address, port numbers, network address translation, TCP, a little bit of operating systems, and also some essentials from IT security. But some of the elements we will also refresh, so we will basically pick up, especially on cryptography and some elements on operating systems. But networking should be somehow basically known. But I think so. Maybe just to start some kind of overview. So, whom of you all have heard communication networks and or a lecture on computer networks, communication networks? Yes. So everybody. How is it in your case? Have you raised your hand? You? Yes. Yes, communication networks. What's your background? Just to know what kind of have you heard the lecture on communication networks, computer networks? So on TCP, IP. Yes, in bachelor's. Yes.
Yeah, computer science. Computer networks, my subject in bachelor's.
Mm-hmm. Okay, and IT security. I think for those familiar faces here that have started here at the university, I saw them. I think also in IT security. How's it otherwise? Did you also have IT security in the bachelor's?
Security.
Yeah, okay. And how is it in you also at security, yes?
Yeah,
Oh?
here in the bachelor's degree.
Okay. So, okay. So, yeah, what my plan is because the last time when the slides were basically put together, and especially when we had 30 students, the background was quite diverse. So for both topics, I will provide a little overview, but just to really recapitulate on what is most important, so that we can we can start to make progress on the more advanced topics, but especially cryptography, and that will be one more essential element that we will pick up to see what all kind of protocols exist to provide various security goals in network security. Okay, so let's one moment. It's a little bit confusing because my left monitor is on the right side here. Okay. Okay, so let's have a look at the topics that we want to cover. So, okay, so this is actually currently the plan. I will have a look how to include some of the wishes that you had, because we also have some kind of opportunities to include in the lecture here. So we'll go through the basics, basically from IT security that we had up to now. We will also cover, so basically we will go first into the networking background and cryptography background. We will pick up then some kind of basic building blocks for security in networking. Go then into different protocols in more detail. And at the end we come to, so the plan was to have confidential computing, so to go more into detail about how to compute on secure data, on private data without having access to it. That will be some kind of also element in this lecture. But basically the goal is always to have a look at what kind of security properties will we have in networked systems. So there are more challenges, especially through the interactions, and that will give us some challenges. But we will also see that most of the solutions that we have are very repetitive. So there's some kind of basic patterns that are very often repeated and used. And one of the goals will be to identify these kind of patterns, so that for new challenges we can also see how to apply them. Okay. So let's have a kind of motivation. Network systems. Why is network security? Why is networking so dominant? What is coming up? So one driving factor is that the mobile and the networks system and world is basically more and more dominant. Smart cities, smart homes, smart grid, smart cars, smart factory. Everything is smart nowadays, and that means that there are some cyber physical systems, meaning some physical systems, something that you can touch, a car, an appliance, any kind of sensors or actuators that are able to communicate. That's the one thing. So the Internet of Things is somehow pushing, meaning that more and more devices are getting connected, and they build some larger systems that allow to basically replicate or create some digital twin of the world. That means that the better you understand what's going on in the world by sensors, by kind of predictive models, you are able to identify flaws and optimize the resource consumption. So the more you know about what's going on, the better you can see where problems are and the better you can optimize. And of course that also means that lots of devices are connected. And the second element is through the industry and economics. Basically, it's also a very globalized world where devices and services and any kind of worldwide market emerges, where basically you can plug and play services from all around the world to build your custom large-scale system that you are envisioning. So it's not uncommon to have maybe some cloud operators in the US, you have some kind of data hosting in China, and you have some kind of privacy-related data management in Europe, and then through the whole globalized networking, you have many exposed services that require basically, in a basic setting, some security. Okay. Okay. I mean, also through the networking demand, basically the slide 1 was motivating. There's a large demand for networking, that you really open up gates to interact with many service providers worldwide. That also exposes potential vulnerabilities that can be misused depending on how well it is basically secured. Let me just see what is the, I mean, that's something new to you maybe. So remote cars, or basically smart cars, or car-to-car appliances can have their weaknesses. There are several studies that show how you can open a car based on how the key that is basically sent by by pressing your car key, how this interacts with the car, and if you observe this, you can basically replicate it, or you identify the patterns, and you can recalculate what should be the next signal. This is one thing, but just taking a car, it's a bigger system in the background. So it's not just, I mean, opening the key, but opening the door, but it's also, if it has some video cameras, you can take influence on what the car sees. So for example, many cars nowadays have some kind of sensor or some kind of video processing on detecting what is the maximum speed limit allowed on the streets, yeah, so that it can automatically give you some warning sign if you are driving too fast. I think this is also now mandatory by law. So, and some cars, some autonomous driving cars have the ability to identify also the obstacles and brake and so on. And you can also take influence on this by specific means, by putting, for example, specific stickers on the maximum speed limit sign, or I mean, there are different examples there as well, how you can take influence on a car and what kind of networking information it spreads. I mean, there are so many application fields where security plays a role, or critical infrastructure, power, industrial control systems, or if there's some public administration, so this Gemeinden, that are frequently attacked, and their machines are basically encrypted, and then ransom is asked for. So there are many attacks that happen through networking, and some of the very critical infrastructures, such as in nuclear power plants, they also require that essential machines are not connected to the internet, don't have any network connection. I also supervised one bachelor thesis in that domain on basically how those machines can be updated, because they don't have any network connection, but this is really the safest element. Some famous network or IT security saying is, if you disable the system, the access to a system, you prevent any kind of activity on it, both good and bad. So by basically stopping a service, no one can misuse it. Okay, so what is network security? It's basically focusing on security in networks, basically all measures for planning, ensuring, monitoring, and managing. What is today? There's some managing of security in networks, including, so first of all, the secure design in network protocols. So basically there are various perspectives on networks. So a network is basically if you have various nodes that are interacting with each other. Yeah. And one element is how these nodes communicate, so the network protocols, that they should maintain some levels of security, meaning that they are either provide confidentiality, integrity, availability, and so on. Then there's, let's break it down. So there's the one-hop communication security, then there's the multi-hop communication security, so that the security either just counts for one-hop communication or for multi-hop and end-to-end communication. Then there's securing network infrastructure and connected devices. This is when we look at how networks of networks interact. There's quite some delay. So how networks of networks interact, how you can make sure that, for example, within the network the data is secured or the network traffic is remaining, I don't know. I know why, yeah, I know why. Maybe I still need some kind of how's it called, this energy providing USB adapter. Does somebody of you have some more powerful? Because otherwise I don't know. It shows me that it's not loading. So does any one of you have some charger for USB charger or so?
No.
Is it in this? Yeah, yes. Just the that one. That's the big challenge. Very nice. So. Okay. This is good. It starts loading. Okay. Just check whether it's still recording. Yep. Okay. So basically we have a look at protocols. We have a look at one-hop communication. How to secure basic. So when I talk about security and securing, typically in this context is the security goals of confidentiality, integrity, availability. These three are in main focus. Sometimes there are also some additional ones like non-repudiation. So what does it mean, confidentiality? I will pick this up when we basically go through the rehearsal about what has been covered in previous security lectures. But let's say, so if we talk in general about security, so nobody else should listen to that communication that is not intended to. Integrity meaning that nobody can change the data without being detected, that is not allowed to. And availability, that the service is available. Yeah, actually, yeah, that cannot be stopped without being allowed to, basically. So in this we can have for one-hop communication, but we can also have for end-to-end communication. And sometimes the protocols that provide these characteristics really have one goal of hop-to-hop communication that is sufficient. Sometimes they want end-to-end communication. Then we have a look at how different networks interact with each other, so firewalls and other kind of organizational measures. And also look at how these surveillance, so especially what's going on between the networks. Is there some ongoing attack happening that we will also have a look at. But first, maybe recapitulate about networks, because just to bring ourselves on the same page. So what do we have? As a first step, we have basically two parts on how a network looks like, or maybe to jump first to the next slide, then it's easier to come back. So how the networks looks like. So if we connect, if we look at the internet, basically it's consisting of two main parts. One is the so-called edge of the network, with all the devices outside. They all have processes running, and they want to interact with each other. So for example, if here we have a server and here we have some clients, then the clients typically want to send some requests to the server. It might be a web browser as a client, it might be a web server as a server, and this is one part of the network. This is the edge of the network. So the hosts running the apps and generating the request and the traffic, and basically asking for data and providing the data. This is one part of the network. And there's the second part of the network, the inner part, so the inner network, which does not have any kind of applications except the goal to, except these kind of routers, which only have one goal. And the only one goal of these devices is to make sure that if here's a message from A and it should be delivered to B, and that the message find its shortest path to the destination node. It can also happen that there are some various paths taken, so it doesn't have always to be the same path. So what also sometimes happens is that packets that are sent out in a specific order, 1, 2, 3, 4, so basically in that direction, are arriving in different orders, or maybe also that there's some kind of I don't know, packet loss or so. Okay, and then we have all the links in between, how these routers are connected. That's fine, but these are the core components, and how they are associated, especially typically you have some kind of private network, a home network, a mobile network, an enterprise network. They manage their internal IP address assignment, and here the routers might be organized in different kind of hierarchical associations. Typically there you have big internet service providers, either local or national or international. Sometimes you have also these content provider networks inside, such as Google, who are very close connected to the internet service providers. But especially this kind of Google, let's have a look. This would be the edge, and again, all routers are part of the global inner network. Okay, and with that, we also see the main characteristics. So the goal is to have this kind of edge network being aiming to being able to exchange information. Data, so basically all hosts at the edge, that's basically the main purpose why these networks exist. So we want to have some request from one host sent to the other host, and the response back. Typically it's about data exchange. There are different kind of ranges how long this networks range. So from personal area network, something some kind of Bluetooth maybe. That's so if I maybe share my Wi-Fi connectivity through Bluetooth, I can connect other devices. Then you have this local area network, either Wi-Fi or Ethernet. Then you have a metropolitan area network. That's typically it's difficult because a wide area network would be okay. So this metropolitan area network, these are some parts of mobile phone cellular networking, and wide area networking. This is the basically bigger kind of network infrastructure from internet service providers, or satellite communication. That would be also potential. Okay, so then we know the applications. We also have a different kind of look. So basically this is the same slide that we have previously had. So we have here at the edge, do we have an animation? No. So it's very strange. So sometimes if I start to draw too early, it switches the page, and sometimes it draws. Yeah. So you have these edge devices here. You have the access network, that's typically your internet service provider, and the internet service provider is part of some kind. So this can be telecom, for example, and you might be at a regional kind of service provider, and then telecom is connected to Telecom France or so, here the Netherlands maybe, and then through Frankfurt and I think Netherlands there's some kind of cable and fiberglass also going to the US. And so somehow all this global networking is happening, and the question is just for your information, where do these different access providers meet? And there are also this kind of internet exchange points. Just so we covered that in the networking lecture, but just to give you an idea. So how does it work that Telecom in Germany is connected to Telecom France and Telecom Netherlands or so? So what they typically do is, while they have their own networks and their own routers, so if this is Germany, they also have some kind of connection to a so-called internet exchange point. So, and there's also France and Netherlands and whoever participate having some kind of connection to this specific point. And at this specific location, this big building, let's say, they have the ability to really physically plug together these connections from the different countries to common switches that are capable to handle the traffic of this size between these very large internet service providers. Are you aware of some of such a local internet exchange point in Germany? So, for example, one of the biggest is diesem. Yeah, this is the German commercial internet exchange, and they are in German. They are here in Frankfurt, and what they basically provide is to really bring together these cables and then connecting it locally here. So it's actually also these are the networks that are connected. So they have 1080 active, so autonomous system networks. So this is basically these autonomous system networks, autonomous systems are such, so you can think of it as internet service providers. And this is also something they can agree locally on who can send traffic to whom for which price. Yeah. So I think also in Europe this is one of the biggest. So it's written who's connected, and this is how the internet is really at the end built together. So you see in Frankfurt there's also the Deutsche Forschungsnetz, who's a internet service provider for universities. There's so there are also companies such as Here. There's Tele2Sverige, so Swedish company. So I mean, University of Mainz. So it doesn't have to be just the very big players connecting at this internet exchange points, but also smaller internet service providers. But I'm also quite sure regular telecom will be also there. Yeah, I think they. Yeah. So this is how basically the internet is connected by having the individual networks of the internet service providers brought together at an internet exchange point to connect with other internet service providers. Okay, so let's also go through the protocol stack, because that we will also need during the lectures to really understand how it is. I think for most of you it might be something that you are already aware of. We will also not go too much into detail. But I think this is one of the core knowledge elements that really needs to be very strong, to have to be understood very well. So what do we have? Typically we start with the bit transmission, the physical layer. Come on. So that means that when, let's say here we have the focus, we have a specific host PC, and it's connected to the router. Typically you are connected, I don't know, by Wi-Fi or by an Ethernet, so a twisted pair cable. And the first goal, the first layer, is to implement the transmission of signals between two hosts, or basically two devices. And the goal is how to emulate a signal so that both parties understand, okay, this is a 0 or 1. So this is the physical layer, and this is the main goal. The question arises in the copper cables, so this twisted pair cables, and coaxial cables, and fiber optics, in Wi-Fi. The question is always, how do I emulate, how do I put a signal on this medium so that it can be understood as a 0 or 1. So the next element is the data link layer and medium access. So data link plus medium access. And the question is, so if we are able from the physical layer to create signals and zeros and ones, as a next step we have to think about what bits to put together to make some reasonable statements. Especially, how do we put into what is the minimum message? So the smallest message, it needs to contain some kind of information on the sender, it needs to contain some information on the receiver, it needs to contain information on what kind of message is this and where to pass it on for further procedure. And this is the data link element, and also if there are some bit errors in the signal, it should be detected and there should be some reaction to it. In most cases it will be dropped and there's a second transmission. So this is part number one. And second, the medium access. This is typically for shared mediums where there are multiple hosts participating in trying to gain access to be allowed to send. So for example, if we all are now in Wi-Fi, we are 8 people, 9 people, all of the smartphones want to send a message through Wi-Fi, but only one is allowed to send a message, so there should be some kind of procedure, how it is decided who can send a message and who not. Okay, then we have realized and implemented one-hop communication because we managed to challenge who can send a message, and we are able to send minimum sized messages with a sender and a receiver and so on. And now as a next step, we need this multi-hop communication. Basically, if A wants to communicate to B, then the whole network should, especially the inner part of the network, should support this routing, meaning that the path to the desired destination is found by the packet. Okay. So, because the challenge is that all of these routers have multiple out ports where the incoming message can be sent to, and as we have also seen here in DH6, for example, where it is listed how many networks are connected at this routing hub. Yeah, if you have 1080 outgoing follow-up networks where you can send an incoming packet to, you need to make a decision on where to pass the message on. And here, for example, there are roughly 300,000 rules. How many, how to decide where the incoming packet should be forwarded to. So this is basically the task of the networking layer, and that realizes this routing, so that the packets really take the quickest path to the destination. Then we have the transport layer, where previously we just sent a message to the host B, but now as a next step we have all these various applications. One example is the web server Apache, and the application on the host A was the browser, so you need to have some kind of application specific addressing, so not just the host should be addressed, but now the application. And as a final step, if we are able to have some kind of application to application communication, then we need to specify what messages should be created, what queries are there, what requests, what responses, and they all need to be specified both in the syntax, so which elements of the message should be present, in which order, how many bits per message part, let's say, and the second part, the semantics. So what are the query options, what are the response options, and how to respond to a respond, and so on. Okay, yeah, why the layering? We'll also see that also in the follow-up we will have this layering also in the security protocols. We will see that there are steps introduced to make it easier to okay, so first, why do we have layerings? So as you have seen, we have this, let's say, 5 layers: physical layer, a data link layer, networking layer, transport layer, and application layer. And one motivation for this is that it allows, basically it focuses on a clear, on clear tasks. And some of the system pieces are clearer to identify what they are for. So if we know that the physical layer only have the task, basically it is required, it offers an interface, it gets some bits and it converts them to signals, sends it to through the medium, and at the other side it receives some signals and converts it to bits. That's what it does. And then the next layer in this reference model could be the data link layer, where it gets a message. Please send this message to one dedicated neighbor in sending surrounding. So it should be already in that it offers a one-hop communication, offering the interface. If you tell me the IP, the address of one neighboring node that I already have a connection to, I will send a message to it, and so on. So by really splitting a big task of networking in smaller tasks, it's easier to maintain, it's easier to provide proposals how to do it, because as the interfaces are fixed, you can exchange the implementation. Yeah, you can change the implementation as long as you maintain the same interface. Okay, and then if you have the layers, let's pass it from that perspective on. So starting, let's say, with the application layer, that requires to specify in very clear detail what kind of, on a very high level, what kind of requests are allowed and what kind of responses are allowed. And one of my examples I like in this context is to have a look at HTTP1 responses. And no, this is not what I saw last time. One moment. So yeah, status codes. Yeah, that's what I wanted to see. So the status codes basically are the response options. Let's have a look at the request options. So HTTP 1.0 had just 3 request options. just get, head, and post. So these were the three request options that were in the first version. So basically, you can ask for a whole HTTP file. You can ask just for the header information, or you can post some information to the web server. These three request options have been there, and the potential responses have been also specified in very clear detail. So you have these various categories: information responses, success responses, redirection messages, client error, server error. And if you go to it, very prominent ones are 200 OK. So that gives you basically the resource that you have asked for, or the header that you ask for. Other prominent examples are moved permanently. So for example, you can redirect the query to another URL. And also very prominent, 404 not found. So you need to specify all kind of response query options, response options. If you receive the response, you need to specify in the kind of state diagram what kind of follow-up interactions you can have. And if both the sender and the receiver know that standard and know what have been specified, they understand each other and can basically do as expected. What kind of interface do we need? So let's say here we get the get, and here we have 200 OK. In order to be able to send this, we need an interface that allows us to send a message from one application. So this round element should be an application to another application on another host. Our web browser should be able to send a message to a web server, and this is done by the transport layer that allows this process to process data transfer. The simplest one is UDP, where you just use a simple port to signal which application is sending the message and which application is the destination. And you can have it more complex with TCP. But this is the main element. So, and in order to achieve this, what interface do we need? We need an interface that allows us to send a message from one host to another host, basically based through the IP address. And this is a multi-hop communication routing protocol that allows to really send a message from Germany to, let's say, I don't know, Alaska or so, depending on the IP address. And the message quickly finds its path. And if we look at ping statistics around the globe, even to the furthest points, it is within 1 second. More often it's around 100 milliseconds or 50 milliseconds. It's more local and regional. So what do we need as an interface in order to enable multi-hop communication? Well, we need to have some kind of one-hop communication. So if you want to have a chain of redirections, then you basically need to have one link as a minimum. And here we have a variety of access opportunities: Wi-Fi, Ethernet, fiber, whatever there is. And the requirement in order to enable one-hop communication is that you can put in some kind of signal on the medium, and it is understood as zeros and ones. Okay. I think. Let's. I think. We will need this because. Okay. Let's have a look at how this looks like, because also, especially in the exercises, we will use quite a lot of Wireshark, and there you can also differentiate according to these layers. So, who of you has already worked with Wireshark? Okay, so basically. So don't be surprised, no problem, because in the bachelor lectures here we also have communication networks. There we use Wireshark. That's the tool that allows you to peek into the network communication, and but this is quite useful to really get some insights. and we will also use it. So just to refresh then the perspective on this kind of networks. So what you typically have is you start with a very simple message. For example, here you have the get message. Come on, get. And you say, yeah, get HTTP 1. I think it's a little bit different, but okay. So what we have is we have the request for an HTTP file, and we send. This is the message. So it just tells, please give me the index file to website. Okay. So what is happening then is, it's at this level we know, okay, this is a browser. We know here this is a browser and this is a web server, because I mean that's who created the messages. So as a next we need to somehow identify the location. So there's some header added for multiple purposes. So TCP, what it does, it first identifies how at the other machine, at the other host, the web server can be addressed. So probably we are using now ports, yeah, especially for the source and for the destination. But also the header in TCP, or yeah, it's TCP typically used, can also have further information. So typically it takes the whole message of the application layer and adds a header to it to create a so-called segment. It also adds information in order to support the detection of lost messages, to detect the reorder issues, but more and more information is added. And then this message is taken and it gets another additional layer, additional header for networking, which now takes the information. So if this is a host, so at this point we had some kind of, let's say the application was associated to port 80. This is just some number that helps the internally received messages basically to be associated to the right program. And here we have one level below the association to an IP address, so that in the global network, host A, let's say globally identifiable by the address A, can send a message to the globally unique and identifiable host B. And this information related to it is put into the header. So typically now the header is growing even further, and this is now called datagram. And now for the next step, where we have basically this one-to-hop communication, then also here a further layer is added. So just assume, let's say in the first link, when I create on my machine now here in the web browser a query to look up a website, I send it over the Wi-Fi to the access point. Is it somewhere here? No, I don't see it. But somewhere is an access point, and because your, let's say, smartphones, notebooks are also in the Wi-Fi, it needs to identify my host sending out the message, needs to tell I'm host XY, so my notebook. So it needs to identify itself in this one-hop neighborhood, and it needs to tell this message is for the access point. In the first hop, as a long-term goal, it is meant for the routing, for the web server, but as a first step, it is meant just for the access point. And then, yeah, we don't have any further headers in the physical layer, because the physical layer just takes this message with these various headers and the core message and transfers it in the signals that is receivable by the access point, let's say. So you can envision it as these various matryoshkas that have an original message, and you put it into another segment on TCP, let's say, datagram on the network layer, and a frame in the data link layer. And once it is received by the next hop, then it packs the frame, let's say, identifies what's the next hop by reading the datagram, and so you really have this adding of further headers layer by layer. Okay. Yeah, just you will see it. So basically, you will see that these headers really grow and contain really relevant information. So if the message comes, it is getting a segment, gets the header, it is getting a so basically, and then every layer. What is the relevant part here is that this part is only relevant for the link layer. This part is only relevant for network layer. And this part is only relevant for the transport layer. So when we will have a look at where to integrate security, then typically it also depends on which layer security protocols are implemented. So as you see, we have here these various layers, 4 layers where we can factually put into some information. And there are representations of security protocols in all of these 4 layers. So you can have, let's say, if here in the link layer, the one-hop communication is the focus, some solutions focus in trying to encrypt only this one-hop communication. Okay. Do you know of some examples where only the one-hop communication is encrypted? And to keep this one-hop communication secure, but once it passes through this one-hop communication, so let's say if the application itself was unsecure and unencrypted, and then it was passed through several hops, it came to a specific link that is encrypted, and then it is passed on after passing this one link unencrypted again. So do you know some examples for this? Where only one single link is encrypted? It's often the first link. So it's, yes, a link is typically a part in a multi-hop communication, so end-to-end, let's say 17 hops. Very commonly, the first link, so the first step is encrypted, and the other further links are not encrypted. Or the first link is often encrypted. Sometimes also the last. So looking, yeah.
Maybe to build up the OP exchanges, for example. For the initial communication setup. And so the first, you need to somehow exchange your keys for the encryption part, and then afterwards everything is encrypted.
Yeah, but afterwards it's not encrypted. So here just the first link would be encrypted. So let's So let's take this kind of example. The browser wants to communicate with Apache web server. Okay. Also the browser will make sure that, but let's say we just think 10 years ago when HTTPS was not predominant, and one of these links is encrypted and all others not. So you see here we have various links. You have here 1 and 2 and 3 and 4 and 5 and 6, 7, 8, yeah. And one of these links is encrypted, and the other 8, the other 7, that's, PowerPoint is such a great tool. So it's really what the user wants. Okay. So one of these links is encrypted and the others are not while calling a network without HTTPS. Which one could be encrypted? Or let's or maybe make it a little bit more obvious. So if we have a second communication, let's take in green. So this is 1, this is 2. Oh, it's almost invisible. Yeah, what you typically have is that the wireless communication link is encrypted. So because you typically you need access a password to join a Wi-Fi network, and if you are, is it true? So what would you say? What ratio of wireless communication traffic is encrypted?
Most networks now are password protected, and even the public access points tend to have some sort of password. Maybe that password is publicly known, but it still has a password, so it is still protected.
Yes.
And WPA3 has an option for a protected network, like an encrypted network without a password.
Mm-hmm. So basically, when the Wi-Fi network uses a password, this kind of shared knowledge is also used to, in a later step, to create a key which is used to encrypt for one-hop communication, and that only affects the communication until the access point, but not further on. And as a second step, let's say network-to-network communication, I mean not network, host-to-host communication from A to B. From A to B, that's also sometimes taking place. That means that all in-between hops are not really, they just forward on the messages, but the encryption takes place between A and B. This sometimes happens if you, for example, want to connect really some remote sites. So typically companies set up some kind of VPN where all of your applications, independent of which application you have, and you want to communicate, all of your traffic is sent to B and exposed there, and the whole traffic should go to B, and basically you can have this side-to-side encrypted communication. Then do you know some example if, so this is host A, sorry, it should be round. So if this is host A in a box and it has various processes, and this is host B and it has various processes, and now only this specific process and this specific process establishes secure communication between each other. Do you know some example for that? Where on your, let's say your machine is A, your notebook, and only one single application establishes a secure connection to one single server in the internet, and your other applications are not secured, let's say. So, yeah, an email client, for example. So if you have enabled, often it is password over TLS or start TLS, but TLS is included. TLS, that we will also have a look at, is basically a transport layer security. If you visit one single website, then your browser establishes one single secure communication channel from your browser to your web server, and this is only for that single application basically valid. And and if you make an email call update to the mail server, it would also create from one application, the email client, to the email server, one secure channel, and retrieve the data. So we have it on various layers. An application could be also something. What would that be? So basically you have A again, you have one unsecure process, and here we have B, one unsecure process. So every message that is put in is delivered without encryption into to the receiving party. So the data is not encrypted by the lower layers. how could you implement some kind of security there? So one idea would be that the messages that you send contain the information that you want. So you send the message 1, which maybe contains a key, and you send the message 2, which contains cipher, and the message themselves. So all of these that is transferred. So the key and the cipher and so on are sent by the lower layers unencrypted. But the messages that you put in, they have been encrypted. So it's, and you can decide for which messages you want to use encryption and for which not. So this would be an application layer security. Okay, we will have for all of these examples, just I want to stress this kind of layering view, because we can have the security procedures implemented on various layers, really. Okay, how does the message then transfer? So basically we have it starting at the application layer at the host A, and it is passed on through the layers. Every time there's a header part added to it, then it is received by the first switch. The switch has various incoming, I mean it has just neutral ports, and whenever a packet comes in, it has to verify which of its outgoing ports it sends it to, and yeah, it also has some switching table. So basically now this outgoing port has been selected. Switches just are transparent to the network, so they are not visible to the source. For example, to every previous hop, they are not visible to the network parties. They just allow to create a larger neighborhood. So let's say if the source A thought previously, okay, with one hop I can reach B, C, and D. Yeah, with a switch, what you can do is if A is connected to a switch, yeah, here's a switch, and here are D, E, F connected, then A doesn't know that it's connected to a switch, it just assumes, oh sorry. A just assumes that it's connected to these neighbors. So they are now available for one hop. So this is basically the switches are invisible in the network topology. It's different from a router. A router is that A sends a message to its first hop, and this is a router. And typically that they are all routers, so it's all router 2, router 3, and so on. Router 17, and then B. And the routers also look into the network layer. They have a look at what's the destination IP address. They decide which of the outgoing IP ports they send a message to. And finally, when the message is arriving at B, it is passed on through the various layers. Every layer checks, am I really the addressed node? And if yes, then I further pass it on upwards. And then the message M is unpacked at the destination process B. Yeah, so there are these layers added. The layers are checked. Networking layer, new networking layers created. And then it is passing on. And every layer takes its information piece that it requires and passes it on the content it has encapsulated. So maybe just 2 slides more. 3 slides. Okay. So in order for all this addressing and layering, we require various addressable elements. So keep in mind, we have, let's say, the one-to-one. We have one-hop communication. Come on. Doesn't want to change to out once. Okay. So in the one-hop communication scenario, you have to think of there are also various other potential recipients, especially if it's Wi-Fi and it's a shared network. So we need to specify who are we that we send out the message, so MAC address A and MAC address B, and we use therefore this media access control address, the MAC address that looks like this 12 hexadecimal characters. They are, we can talk about how they are assigned. Sometimes they are fixed in hardware, sometimes they are modifiable, but typically what you do is, if you have this one-hop communication, in the one-hop communication the source MAC address needs to be told and the destination MAC address needs to be told, and only they are used to identify who's the sender and who's the recipient in this one-hop communication environment. And then on a global scale, we need some. We have the IP address that is locally, that is globally routable. So these are some kind of IPv6, 444 addresses. That these ones are local. These are some IPv6 addresses. They are typically hierarchically assigned. So typically, if you want to participate in global routing, you need some contract with an ISP, with an internet service provider that's already part of the network. And when you set up a contract with them, you pay them money to get an internationally routable IP address and the commitment to process your traffic. Yeah, and this should be and must be globally unique. And the last point is, if we have the applications, let's say you are now able with IP addressing and IP routing to send messages across the globe to various machines. But on these machines there are multiple applications running. So you need to tell them, okay, this is application 1, 2, 3. I want to communicate to application 4, 5, 6 on the recipient side. And therefore we use the port numbers. And basically there's just some kind of agreement which port numbers to use. That's, nobody can force you to use them. But let's say port number 80 is for for HTTP, and you assume that if you call with your browser a web server under port 80, the browser is registered under the port 80 to receive messages. So by this you can also, for example, register various ports of web servers at your local machine that individually show different kind of websites, because this is a different web server that is addressed if you use a different port. Okay. What will we do next? I mean, in the next exercise. So first of all, in the exercise we will have short interaction with Linux and to see how to use it. But after that, we will also start with Wireshark in the follow-up lectures, so that we can really really look into actual security protocol setups and actual attacks. That will be the next step to look into. And I'm looking forward to see you in the exercises. I will update the slides, especially with the dates at the front. Yeah, and yeah, happy to have you here, and it will be a nice semester. So thanks for listening, and see you next time.